Now that you know what concurrency is, let's look at the common problems it brings. The first problem is lost updates. This happens when two transactions try to update the same data and we don't use locks. In this situation, the transaction that commits later will override the changes made by the previous transaction. For example, let's say that we have two transactions that try to update the same customer. One tries to increase the points, the other tries to update the state for this customer. Here's our customer record. John in New York with 10 points. Now we have two transactions. Transaction A that tries to update the state of this customer, and transaction B that tries to update the points for this customer. These two transactions occur at the same time. This is the customer record that both these transactions see. Now, let's say transaction A updates the state, but it hasn't committed yet. At the same time, transaction B updates the points. Now, the transaction that commits last will overwrite the changes made earlier. In this case, if transaction B commits last, we will lose the update made by transaction A. How can we prevent this from happening? We use locks. So as you saw in the last lecture, by default, MySQL uses a lock-in mechanism to prevent two transactions from updating the same data at the same time. They will run in sequence one after another, and we'll have both updates. Let's look at the next common concurrency problem. Dirty reads. A dirty read happens when a transaction reads data that hasn't been committed yet. For example, transaction A changes the points for a customer from 10 to 20, but before it commits the change, transaction B reads this customer and based on the customer's points makes a decision. Let's say for every 1 point, it gives a $1 discount to the customer. So it's going to give this customer a $20 discount. Now, what if transaction A rolls back before transaction B completes? Transaction B would have data that had never existed. In other words, this customer never had 20 points, this was never committed to the database, and transaction B gave this customer a $20 discount. So in this scenario, we have read uncommitted data in transaction B. Our data was dirty. Now, to solve this problem, we need to provide a level of isolation around our transactions. So data modified by a transaction is not immediately visible to other transactions unless it's committed. The standard SQL defines 4 transaction isolation levels, which you're going to learn about soon. One of these is read committed. When we use this isolation level for a transaction, that transaction can only read committed data. With this, we won't have dirty reads. Now, what if the data gets changed after our transaction completes? It doesn't really matter. What matters is that any data that we read is committed at the moment it is read. If we make a business decision in a transaction, we base our decision on valid, committed data. The data can change later after the transaction, and our transaction shouldn't worry about that. So when we set the isolation level for a transaction to read committed, that transaction will only read committed data. In the next lecture, I'll show you how to set the isolation level. Now let's look at another concurrency problem. Non-repeatable reads. So by adding more isolation to our transaction, we can guarantee that our transaction can only read committed data. But what if during the course of a transaction, we read something twice and get different results? For example, transaction A reads our customer's points. It sees that this customer has 10 points, so it will make a business decision based on this value. Now, before transaction A completes, another transaction, like transaction B, updates the points for this customer to 0. Now, back to transaction A, we read the points for this customer one more time, perhaps as part of a subquery. Now, in this transaction, we have read the points twice, and each time we have seen a different value. This is a non-repeatable or inconsistent read. How should we handle this situation? Well, we can argue that at any point in time, we should make decisions based on what is the most up-to-date. If that's the case for a business scenario, we don't really have to worry about anything here. But we can also argue that at the time our transaction started, this customer had 10 points, so we should have given them a $10 discount. If the points change during this transaction, we shouldn't see the changes. We should see the initial snapshot. If that's what we want, then we need to increase the isolation level of our transaction. We need to isolate it from other transactions such that changes to the data aren't visible to our transaction. The SQL standard defines another isolation level called repeatable reads. With this level, our reads are repeatable and consistent, even if the data gets changed by other transactions. we'll see the snapshot that was established by the first read. And the last common concurrency problem is phantom reads. Imagine in transaction A, we're querying all the customers who have more than 10 points. Perhaps we want to send them a special discount code. Now, at the same time, transaction B updates the points for another customer that was not returned by our query. So this customer is now eligible for this discount code, but at the time we queried the customers table, we didn't see this customer. So after transaction A completes, there is still one eligible customer that didn't receive this discount code. This is what we call a phantom read. Phantom means ghost. So we have data that suddenly appears like a ghost and we miss them in our query because they get added, updated, or removed after we execute our query. How can we solve this problem? Well, it depends on the business problem we're trying to solve and how important it is to include this customer in our transaction. We can always re-execute transaction A at a later time, and this customer will also get a discount code. Not a big deal. But if it's absolutely critical to include all eligible customers in our transaction, we'll have to make sure that no other transactions are running that can impact our query to find the eligible customers. For this, we have another isolation level called serializable, and this will guarantee that our transaction will be aware of changes currently being made by other transactions to the data. If there are other transactions modifying the data that can impact our query result, our transaction has to wait for them to complete. So transactions will be executed sequentially. This is the highest level of isolation that we can apply to a transaction, and it gives us the most certainty in our operations. But it comes with a cost. The more users and concurrent transactions we have, the more waits we're going to experience, and our system is going to slow down. So this isolation level can hurt performance and scalability. For this reason, we should reserve this only in scenarios where it's absolutely critical and necessary to prevent phantom reads. Now, if all this sounds overwhelming, don't worry. We're going to review all these concurrency problems and how to solve them again. Later in this section, I will show you each concurrency problem and how to solve it using a transaction isolation level.